I tutor physics, but I hate physics, and there is a set of problems that comes back again and again and again to haunt me, no matter how many times I learn or teach physics. And I'm going to start this series called Annoying Physics Problems because they are, lo and behold, annoying. So these are like very specific problems that for some reason come up in every single physics class. And the example we're going to do today is called the scale and the elevator. So for some reason, physics teachers like to think that we like to weigh ourselves, and furthermore, they like to think that we like to weigh ourselves in public elevators. So in these types of situations, there is a person on a scale, and this scale is a physics scale. It measures in newtons, and it's in an elevator that is moving some various amount. So this elevator has two conditions that it can have. It can either be accelerating or it can be not accelerating. And you're quickly going to learn, as you learn physics, that if this elevator is not moving, and if it's moving at a constant velocity or not accelerating, that's basically the same to us. Because forces, if there's a net force, they're going to cause an acceleration. So if this thing is going zero, or if it's going at a constant velocity, even if it's going up or down, what you're going to see on this scale is this person's weight. They're not going to be flattered. They're not going to be disappointed. So here's this person. I'm going to weigh them at 65 kilograms, or that's their mass. So if this elevator is going zero velocity, or if it's going constant velocity, then the forces acting on this person, they're going to be gravity and the normal force. And that's going to be the case always. So there's gravity, which is mass times the acceleration due to gravity, and there's the normal force, which is equal to the negative of these things. Right? So in this case, if there's zero velocity, or if they're going at a constant velocity, this scale, which shows the normal force, is the point of these problems, is that the scale is going to show the normal force is going to be equal to 65 kilograms times 10 meters per second squared. And I'm going to continue to use 10 in these videos even though it's technically 9.8. Okay, so that's going to be 650 newtons. That's the default. So what happens if this thing is accelerating downward? So let's say the downward acceleration is equal to 5 meters per second squared. So in this case, let's say that this is my person. This is what we call a free body diagram, where basically we take a point and that represents our thing, and then we're going to have forces on it. So this is the force due to gravity. This is going to be the normal force, which we don't know. And they're going to add up to a net force, which is just the total. So the net force is equal to gravity minus the normal force. And the reason that I'm doing it this way, gravity minus the normal force, is that the net force is downward and gravity is downward. So the difference between gravity and normal force is going to end up like going downward. So positive in this case, I'm just making that down. So the net force is going to be the mass of the person times 5 meters per second squared. And that's going to end up equaling the mass of the person times gravitational acceleration minus the normal force. So I want to make everything positive. I want to make normal force positive, so I'm actually going to add normal force to both sides and subtract this other side. So this can distribute I want to stop using units here, but those are accelerations in the parentheses. So the normal force we can now say is going to be the mass, which is again 65 kilograms is the mass of our person, times 10, which is acceleration due to gravity, minus 5. So if our elevator is going downward, what's going to happen is that the normal force, which is the value we see on the scale, is going to end up being 65 times 5 equals, well, 60 times 5 is 300, 5 times 5 is 25, 325 newtons. So remember that our default when we were not moving or when we were moving at a constant velocity was 650 newtons. So if your elevator is accelerating downward, what's happening is you're seeing a smaller weight on your scale. So what happens if we're accelerating upward? So let's say we're accelerating up with, again, 5 meters per second squared. Same deal, except now up wins. So I'm going to say that the net force is equal to the normal force minus the gravitational force. So mass of this person times the acceleration, the net acceleration is 5 meters per second squared, equals normal force minus the gravitational force. Now in order to get everything to be positive, I'm just going to do gravitational force, which I should have put down as mg here. I'm going to add that to both sides. It's going to look like that, and g is going to end up being 10, so it's going to be 5 plus 10. So this is going to get us a normal force of 65 kilograms times 15 meters per second squared, which is going to get us a normal force, or what we see on the scale, 950 newtons. So now we see more on the scale if the elevator is accelerating upward. And the reason why is because now we have more of a normal force in order to not only be equal to gravity, but to overcome it and accelerate us upward. So that is never ever going to apply to you in real life, but may apply to you on a physics test. Hope it helped.